Assalamu alaikum dear students. Okay, today we are going to discuss some consequences of Sylow-p theorems, and before this we have discussed Syllow's p subgroups and Syllow's theorems and their proofs. And to understand proof of Syllow's third theorem, which was given in lecture 13, I suggest to watch lecture number 12, where we have discussed the statement of Syllow's third theorem, that how can you tackle this statement and what should be the idea to prove Syllow's third theorem, because there I have given complete layout to understand its statement with the help of examples, and to understand the idea that how can we prove. I have sketched few lines where through which you can find its proof so easy. Then after watching lecture 12, if you are watching lecture 13, it would be so easy. Okay, thank you. Here I want to discuss something regarding in group 3.1, and everybody know about Lagrange theorem, that Lagrange theorem was if G is a finite group and H is a subgroup of G, then the order and index both are in fact the divisors of the order of group G. So there was a popular question. There were two popular questions. Sometimes people call them that converse of Lagrange theorem. What is the converse of Lagrange theorem? It was, if a number D divides the order of the group G, then can you always find a subgroup of order D? This was the popular question. And we are giving the answers of these two questions. In fact, the first question was, if D is a divisor of the order of a group G, can you always find a subgroup of order D? What I am saying, that if D is dividing the order of G, can you find a subgroup H in G of order D? Can you always find? And second question was, if you can find a subgroup of order D, can you find the number of subgroups of order D? So these were the two popular questions. The first question is also known as the converse of Lagrange theorem, and second is in fact the cardinality of such groups, right? In first theorem, Syllow's first theorem, we have given the idea that if a prime number P divides the order of a group G, then G has a Sylow-p subgroup. Okay, and before this theory, we have some examples where the answer was in negation, because if D is a divisor of the order of a group G, then this is not the case always that G has a subgroup of order T. Like I am giving you some example. In group 3.1, the chapter name was permutation. We have a very popular theorem. What was that? n greater than or equal to 5 is simple. So let's revise a little bit. What do you mean by simple? You know, simple, a group is said to be simple if it has no proper normal subgroup. No proper normal subgroup. What do you mean by simple? Simple means having no proper normal subgroup. You know, two subgroups are the trivial subgroups. They are one is identity, and the other is group itself. They are the trivial subgroups, or you can say improper, I don't know. But proper subgroup whose order is greater than 1, and which is whose order is greater than 1 and not equal to the order of G, it's a proper subgroup, right? So n greater than 5 is simple. So look at A5. Yeah, order of A5, you know that order of A5 is 5 factorial by 2, which is 120 by 2, which is 60. Now look at this example. You know 30 is a divisor of 60. 30, if you take d is equal to 30, if d is equal to 30, then d divides 60. And if you have a subgroup of order 30, suppose you have a subgroup H of order 30, then index of H in A5 would be equal to order of A5 divided by order of H, which is 60 by 30, and which is equal to 2. And you know that if the index of a subgroup is 2, then it is normal. It is a normal subgroup. It's also very popular term. This was the first definition. The second definition, if index of H, if in G is 2, then H is normal in G. We have a very popular theorem in our course of Group 3.1. So look at this. The order of A5 is 60, 30 is a divisor of 60, and if there is a subgroup of order 30, then H would be normal. H would be normal. Also, it would be a proper normal because order is 30. It is greater than 1 and lesser than the order of the G, order of A5. So, in this case, A5 would not be simple because it has a proper normal subgroup. But we are saying that having no proper normal subgroup is simple. So, this means that H is normal in A5. This means that A5 is not simple while order of H is not equal to 1 and not equal to 1, and order of H is less than 60 is not simple, a contradiction. Okay, so I want to tell you a little background why we are studying Sylow's theorems and what was the idea behind in Sylow's mind, that why he had established these words, Sylow 1, Sylow 2, Sylow 3. In fact, there was two popular questions in the history. The first was, if a number d divides the order of a group G, can you always find a subgroup of order D in G? The answer is no. The answer is no. This is not the case, in fact. This means that the converse of Lagrange theorem is false in general, right? Because, you know, A5 is simple, but if 30 is a divisor of 60, and if there is a subgroup of 30 in A5, then it would be normal. In that case, A5 would not be simple, a contradiction to this very popular theorem. That's why the first question is wrong. Of course, this is not always the case, that if D is a divisor of a group G, of a finite group G, then G has a subgroup of order D. Okay, but in cyclic group, you remember, we have learned that if D is a divisor of a cyclic group, then that cyclic group always has a subgroup, a unique subgroup of order D. I mean, whenever D is a divisor of a cyclic group, then D must has a subgroup, then cyclic group must has a subgroup of order D, and it has exactly one subgroup of order D. So, in cyclic group, the converse of Lagrange theorem is true, and also there is no question of number of subgroups of order T, because whenever D is a divisor of the order of a cyclic group, then that cyclic group must has exactly one subgroup of order T. Okay, but this question is still pending for general subgroup, and this question had been addressed by Sylow's third theorem. Okay, Syllow's third theorem says that k, the number of Sylow-p subgroup. In Sylow first theorem, we are saying that if p is a divisor of the order of any group, then that group must has at least one Sylow-p subgroup. And Sylow 3 says that the number of such Sylow-p subgroups is k, and k is a divisor of the order of the group, and k congruous to 1 mod p. Also, I suggest to understand the proof of Sylow's third theorem, which I have delivered in lecture 13. I suggest to watch lecture 12 first, because in lecture 12 I have explained the statement with the help of examples. Then we have given discussed a layout to prove how to prove Sylow's third theorem. So better to understand Sylow's third theorem, I suggest to watch first statement and explanation, discussion of Sylow's third theorem, which was given in lecture 12. Then see the proof of lecture 13, which is Sylow's third theorem. Okay, right. So now we understand why we are studying. Someone asked me that why we are studying Sylow's theorem. So I have given you idea that these were two popular questions in the history, that if D is a divisor of the order of a group G, can you always find a subgroup of order D? So the answer is negation in general, but in cyclic group this is true. And the second question was, how many number of subgroups? If there is a subgroup of order D, where D is a divisor of the order of G, then how many subgroup? Then can you find the number of subgroups of order D? So this was addressed in Sylow's third theorem. Okay, so that's why we are studying the Sylow's theory. Now I want to give you few of the consequences. These are the very popular consequences in the form of theorems, right? So I am going to elaborate these results in this lecture. The first one is, okay, the first one is, if P is a P subgroup of finite group G, then P is contained in a Sylow-p subgroup. So this is very easy to understand, because you know that a Sylow-p subgroup, the order of a Sylow-p subgroup is P power alpha, where P power alpha is the highest number, which is the divisor of the order of G. While any subgroup of order P is a P subgroup, right? For example, if the order of a Sylow-p subgroup, if the order of a Sylow-p subgroup H, let's say, if order of H is equal to 5 power 4, you know, and H is a Sylow-p subgroup, then you may have a subgroup of order 5, a subgroup of order 5 square, a subgroup of order 5 cube. But we have to show that every P subgroup, every 5 subgroup is contained in H. You may have a subgroup, this is a Sylow 5, this is a Sylow 5, H is a Sylow 5 subgroup, and if K is a subgroup, order of K, where K is a subgroup, is 5 R5 square, R5 cube. You have to show that K is contained in H. This is our first term. The first term says that if H is a Sylow-p subgroup and P is a P subgroup, then you have to show that every P subgroup is contained in its Sylow-p subgroup, right? So you can understand with the help of example. Let's say if you are taking C12, you know this is 2 square into 3, 2 square into 3. Now it has a Sylow-p by Sylow's first theorem. It has a Sylow-2 subgroup and it has a Sylow-3 subgroup, right? And you know that Sylow-2 subgroup is of order 2 square, order 4. So here h, order of h is in fact 2 square. And you know that in a cyclic group, every subgroup of order D is unique, right? Because 4 is the divisor of C12, then C12 has exactly one subgroup for order 4, which would be a Sylow-p subgroup, in fact, right? So here H is in fact no, here H is in fact E of order 4. You know, A cube, A6, A9 and A12 is equal to, you know that C12 is in fact C12 is equal to A psi that A12 is equal to E, right? So here H, this is a Sylow-p subgroup, and there is a subgroup K, which is, you are saying P. This is also a subgroup EA6. It's a 2 subgroup because order of P is 2. It's a 2 subgroup. It's a P subgroup. It's also P subgroup, but is a Sylow-p subgroup as well, because 4 is the highest number, which is in fact the divisor of C12. So that's why H is a Sylow-p subgroup. H is a Sylow-p in C12. So P is a 2 group, 2 subgroup. In C12. Look at this. You have a Sylow-p subgroup and you have a Sylow-p subgroup, but you see this is contained in H. So here P is contained in H. Now look at this statement. If P is a P subgroup of finite group G, then P is contained in a Sylow-p subgroup of G. Means that every P subgroup is contained in a Sylow-p subgroup, right? Okay, this further. Now we need to prove this. Okay, similarly, if you take D4, whose order is 8, which is 2 cube, so D4 is itself a Sylow-p subgroup because the 2 cube is the highest number. There does not exist any Sylow-p subgroup of order 4 because 2 power 4 dividing D4 and 2 power cube is also dividing D4. So you cannot find any Sylow-p subgroup of order lesser than 8 in D4. But there are Sylow-p subgroups. There are P subgroups of order 4 and of order 2. We know that you have P here, E, B, A square, B. Then order of P is 4. That is 2 square. It's a 2 subgroup. It's a P subgroup. And here it's contained in D4 because D4 itself is a Sylow-p subgroup, right? Similarly, you could have P1 as well, E A square, yes. This is also a subgroup, E A square, and P1 is also contained in D4. So both are contained in a Sylow-p subgroup. In fact, here D4 was a Sylow-p subgroup. But if you are finding a group for which D4 is a factor, then D4 being a factor of that is a Sylow-p subgroup, and these two are the subgroup of D4. So again you can view this theorem in a broader spectrum. I will explain when I will discuss applications of Sylow's theorems. Okay, but now I want to discuss some consequences of Sylow's theorem. Okay, this is the first consequence. Now I want to prove this. So proof is so simple. Right. let order of P is equal to P power U, P power R, you can say P power N1, or say beta. You know, P is a P subgroup, here P is prime, and this P is stand for P subgroup. You can replace this by K. This is a P subgroup. Take order of P is equal to P power beta, and order of H is equal to P power alpha. Of course, beta is lesser equal to alpha because it's a P subgroup, and here P is the same where P is prime number. Here P is prime. P is prime, or you can say P is fixed prime. So that P is same. This P and this P both are same. P is a fixed prime. Okay. We have taken capital P as a P subgroup and H as a Sylow-p subgroup, right? Then by Lagrange theorem, order of G, say this is equal to N, and also you can assume that order of G is equal to then index of H in G, say order of G is equal to N, because since G is a finite group, so you may assume that this is equal to N, and index of H in G is equal to N, then N is equal to P power alpha M. Of course, M and P would be, M and P are relative prime. I already have explained in my previous lectures. Otherwise, P is a divisor of M. Then here you can write P M1. This would give you P power alpha plus 1 is a divisor of N, which would be a contradiction. So that's why this prime number and M are relatively prime. This is very simple because every number with a prime number has either P divides M, or P and M are relatively prime. So here, when you are writing by Lagrange theorem, N is equal to P power alpha M, then of course M and P are prime to each other. Okay. Now again consider the double coset decomposition of G by using these two subgroups P and H. We can write, let there be R possible double cosets modulo PH. You may assume, let there be or possible double cosets decompositions modulo PH, then we have discussed this thing a number of times. You can understand from double coset decompositions from Sylow's second theorem and from Sylow's third theorem as well, right? So you know very well, we are getting G is equal to union of I varies from 1 to R, P, A, I, H, right? So this implies order of G is equal to summation I varies from 1 to R, order of P into order of H over order of P intersection, right? AI, AI H, AI inverse. You know, since this double coset decomposition is a partition of G, and these are the mutually disjoint possible or double cosets, so that's why their unit is the entire group G, and they have no common intersection to each other. So because principle of inclusion exclusion, you can write directly like this. So this is equal to n is equal to summation I will from 1 to r p power alpha, this is p power beta over qi. You know, say qi is in fact order p intersection ai h ai inverse. Okay, so from here you can write n by p power alpha, which is equal to summation I will from 1 to r p power beta over, this is right, again beta over qi, say number 1, and you know this is equal to, again you know that alpha is independent of this summation, because summation is over r, I is over r, summation is over I, and I varies from 1 to r. That's why p power alpha is independent of this summation, so you can divide. And what is n power p power alpha? This is your capital, this is your small m index. Okay. So this implies m is equal to summation p power beta over qi, I varies from 1 to r. This is equal to m one to r p power beta qi. Okay, again please watch the proof of Syllow's second theorem and Syllow's third theorem to understand the idea. And you know that each term on the right side is either 1 or divisible by p, is a multiple of p. So for sake of convenience, assume that the first term is 1. Okay, so clearly since qi is equal to p intersection order of p ai h ai inverse, order of qi is equal to order of this, and this is the p group. This one is you know, conjugate to h, Sylow-p subgroup, so order is p power alpha, and this is a p subgroup. Anyhow, this is a subgroup of p and also a subgroup of Sylow-p, so it is a p group, right? Where qi is equal to some p power, you know, you can write alpha I, being the order of a P group. You can say that since P is a P group, P intersection AIH, AI inverse is a P group. Is a P group, is a subgroup of a P group. Is a subgroup of P groups. You know, both are P groups. This is a P group, this is a P group, and this intersection is a subgroup of P groups. So that's why you assume that its order is P power alpha I, right? So you are getting hence M is equal to summation P power beta over P power alpha I is from 1 to R. Here P same, which is equal to summation I is from 1 to R P power beta minus alpha I. Now that's why if beta is equal to alpha I, then the term is 1, right? R beta is of course is the order of your P group, so must be greater than alpha I, greater than equal to alpha I. If beta is equal to alpha I, then this is 1. So clearly each term on right hand side is either one or multiple of P prime P. Okay, look at this again. It's the order of the intersection of P subgroups. So that's why you can write its order P power alpha I. Now this becomes P power beta by P power alpha I. This is like this, like this. Now beta, basically P power alpha I is the order of a subgroup. Either P power beta is equal to alpha I or beta is greater than alpha I. If beta is equal to 5, then it is 1. That's why on the right side, either you can see that some power of P or it is 1. That's why I am writing. Clearly each term on right side is either 1 or multiple of P. So without any loss, you assume that the first one is 1, right? Without any loss, assume P power beta minus alpha 1 is equal to 1. So this implies P power beta over P power alpha 1 is equal to 1. So this implies P power beta would be equal to P power alpha 1. Here, you know what was P power alpha 1? Where order of H is equal to P power beta and order of H intersection order of P, you know, order of P is equal to P over beta and order of P intersection A, H, A inverse, of course A1 inverse is equal to P power alpha 1. Now look at this. Order of P over beta, now order of this, where this is a subgroup of capital P, here capital P is a P subgroup and this P is prime number. So, but P intersection A1 H A1 inverse is a subset of P. Now again we are using the same logic. If you have a subset of the same order as that of its superset, then it means that both are same. You know, P is P intersection this one is a subset of this with same orders. P power of beta is equal to P power alpha 1. You know, P power beta is equal to P power alpha 1 with same order. That's why, hence, P intersection A1H A1 inverse would be equal to capital P. Look at this, right? Its order is P power beta, its order is P power alpha, and both are same. That's why, and also this is a subset of this one. If this one is a subset of this with the same order, then you can say that these two are equal in fact. So what does it mean? That if A intersection B is A, then this means that P is contained in A1A inverse. But you know that A1H A1 inverse is conjugate to H, where H is a Sylow-p subgroup, so this is also a Sylow-p subgroup. Hence you see that P, capital P is contained in a Sylow-p subgroup. But A1H A1 inverse is conjugate to H, so it is a Sylow-p subgroup of G as well. This is by second Sylow's theorem. Hence, P is contained in a Sylow-p subgroup. And this completes the proof. You see that if P is a P subgroup, then it is always contained in a Sylow-p subgroup. Yes, we have completed the proof. Okay, thank you very much. We will discuss next of the consequences in our next lecture. Thank you. Allah Hafiz.